NASA's Planetary Defence Coordination Office has identified 28 asteroids capable of causing human extinction. However, their classified models suggest we have less than a 30% chance of successfully deflecting one if we had less than a year's warning. If a planet-killer asteroid were detected tomorrow on a collision course with Earth, would we actually be able to stop it? The disturbing answer is, probably not. The public perception of asteroid defense, shaped by Hollywood films like Armageddon and Don't Look Up, bears little resemblance to the sobering reality facing the scientific community. We're not just unprepared, we're dangerously vulnerable, and the statistics tell a story far more frightening than fiction ever could. Our planet bears the scars of cosmic impacts going back billions of years. The dinosaurs were wiped out by an asteroid estimated at just 6 miles wide. Tiny by cosmic standards, yet devastating enough to trigger a mass extinction event. But that wasn't a freak occurrence. It was just the most recent major impact in Earth's long history of cosmic bombardment. Statistical analysis of impact craters and near-Earth object tracking data suggests that extinction-level impacts occur roughly every 100 million years. That might sound reassuring until you realize the dinosaur-killing impact was about 66 million years ago. In cosmic terms, we're already in the danger zone, statistically overdue for another catastrophic impact. Even more alarming is what scientists call the detection gap. Despite significant advances in asteroid tracking technology, we can currently only account for about 40% of potentially hazardous near-Earth objects larger than 140 meters. For objects approaching from the direction of the Sun, we're essentially blind. In 2013, a meteor just 20 meters wide exploded over Chelyabinsk, Russia, injuring 1,500 people, and we didn't see it coming at all. It arrived from the direction of the Sun, exploiting a massive blind spot in our detection capabilities. Now scale that up to an asteroid hundreds of times larger. The National Academy of Sciences estimates that at any given moment, at least 3 potentially hazardous asteroids cross Earth's orbit completely undetected. The Apophis asteroid, named after the Egyptian god of chaos, illustrates this problem perfectly. When first detected in 2004, initial calculations gave it a 2.7% chance of hitting Earth in 2029, the highest probability ever assigned to a potential impact. Further observations eventually ruled out a collision, but for a brief period, scientists were genuinely concerned about a catastrophic impact with less than 25 years of warning. The unsettling truth is that our asteroid detection infrastructure remains woefully inadequate. The Planetary Defence Coordination Office operates on an annual budget less than the cost of a single Hollywood blockbuster about asteroids. But even if we detect a planet killer in time, our most obvious defense strategy could make things catastrophically worse, and here's why. The first solution that comes to mind, and the one popularized by films, is to launch nuclear weapons at the approaching asteroid. On paper, this seems logical. Use our most powerful weapons to either destroy the threat or knock it off course. But the physics tells a much more complex and disturbing story. Asteroids aren't uniform objects. Many are what scientists call rubble piles, loose conglomerations of rock and metal held together primarily by their own weak gravity. Detonating a nuclear device against such an object wouldn't destroy it as depicted in movies. Instead, it would likely fragment the asteroid into multiple smaller pieces, potentially creating what NASA scientists grimly call a shotgun blast effect that could be even more devastating than the original single impact. Even for solid metallic asteroids, the nuclear option presents enormous challenges. The energy from a nuclear explosion in the vacuum of space would primarily be released as radiation, rather than the blast wave we associate with nuclear weapons on Earth. This radiation would vaporize only the surface material it directly contacts. For a large metallic asteroid, this might alter its course by less than 1/100%, nowhere near enough to avoid Earth. The fundamental problem is one of physics. The energy needed to meaningfully deflect a large asteroid increases exponentially with the asteroid's mass, and with how late we attempt the deflection. Waiting until an asteroid is 6 months from impact might require 10,000 times more energy than acting 10 years in advance. The window for effective intervention is shockingly narrow, and the precision required is beyond our current capabilities. Asteroid deflection is often described as trying to hit a bullet with another bullet. Except both bullets are traveling at 20,000 miles per hour and the target bullet might be tumbling unpredictably. The 2021 DART mission successfully demonstrated that we can hit an asteroid with a spacecraft, but it altered its target's velocity by less than 1 centimeter per second. For context, a planet-threatening asteroid would need to be deflected by at least 35 times that amount to miss Earth, even with years of advance notice. With less than a year's warning, the required deflection would be physically impossible with current technology. Beyond the technical challenges lies a coordination problem that few discuss openly. An asteroid deflection mission would require international cooperation on an unprecedented scale, involving split-second timing and perfect execution. The geopolitical hurdles alone are staggering. Who decides the deflection strategy? Who pays for it? What if the planned deflection could potentially shift the impact from one nation to another? These aren't just administrative questions, they represent critical failure points in any real-world deflection scenario. The technologies that might actually save us exist only on drawing boards, and what they would require is almost beyond comprehension, both in terms of engineering scale and economic investment. The most promising technological solution isn't blowing asteroids up. It's gently nudging them over time using what scientists call gravity tractors. These theoretical spacecraft would hover near an asteroid, using their own mass to gradually alter the asteroid's trajectory through gravitational attraction. No physical contact required, no risk of fragmentation, but the engineering challenges are staggering. To meaningfully affect even a medium-sized asteroid within a reasonable timeframe, we would need to build spacecraft orders of magnitude larger than anything humans have ever constructed. A gravity tractor capable of deflecting a kilometer-wide asteroid within 5 years would need to be roughly the size of the International Space Station, cost upwards of $100 billion, and require assembly in orbit. We would need to develop new propulsion systems capable of maintaining precise positioning relative to a tumbling asteroid for years on end. The computational requirements alone would exceed anything we've built for space applications. And most critically, we would need to deploy this system years before impact, meaning we'd need to invest in building it now, before any specific threat has been identified. It's a massive investment against a probabilistic future threat, something human institutions have historically been terrible at prioritizing. Another theoretical solution involves kinetic impactors, essentially hitting the asteroid with massive projectiles to alter its course. While we've demonstrated this capability on a small scale with the DART mission, scaling it up presents enormous challenges. To deflect a civilization-ending asteroid with less than 2 years' warning would require impactors weighing thousands of tons, payloads far beyond our current launch capabilities. We would need to develop new heavy-lift rockets specifically for planetary defense, maintain them in a constant state of readiness, and be prepared to launch multiple missions in rapid succession. The estimated cost for this capability starts at $200 billion, and could easily reach trillion-dollar levels when including the necessary detection systems and ready-to-launch infrastructure. Even more exotic solutions have been proposed, like focusing solar energy using massive space-based mirrors to essentially boil off part of the asteroid's surface, creating a natural rocket effect that would push it off course. Or deploying paintballs to change the asteroid's albedo, altering how it absorbs solar radiation, and gradually shifting its orbit through the Yarkovsky effect. But all these solutions share the same fundamental limitation. They only work with years or decades of advance notice. And this brings us to the most terrifying reality about asteroid defense. It's not primarily a technology problem, it's a timing nightmare. Our detection capabilities give us dangerously little warning for the most threatening approach trajectories. Astronomers call them short warning scenarios, and they represent the true nightmare of planetary defense. Certain approach trajectories, particularly those coming from the direction of the sun, might give us less than 72 hours from initial detection to impact. In such scenarios, even with perfect international cooperation and fully developed defense systems, physics itself would prevent any meaningful intervention. The sheer energy required to deflect an asteroid on such short notice exceeds anything humans could feasibly deploy. We would have detected our extinction event with just enough time to know it was coming, but not enough time to stop it. This isn't just theoretical pessimism. In 2019, asteroid 2019 OK passed within 45,000 miles of Earth, about 1/5 the distance to the Moon, and was detected only 24 hours before its closest approach. Had its trajectory been slightly different, we would have had 1 day's notice before an impact capable of destroying an entire metropolitan area. In 2020, asteroid 2020 QG came within 1,830 miles of Earth's surface, the closest recorded non-impacting approach, and was detected only after it had already passed by. These weren't small objects. They were city killers that our detection systems simply failed to spot in time. Some scientists have suggested pre-deploying interceptor systems in space, ready to respond to short-warning scenarios. But this too creates new risks. Orbital defense platforms capable of deflecting asteroids would, by definition, also be capable of redirecting them toward specific targets on Earth. The weaponization potential is obvious and alarming. The geopolitical complexities of deploying such systems might actually increase the likelihood of human-caused disasters while attempting to prevent natural ones. Even a successful deflection carries risks. Altering an asteroid's trajectory by even a fraction of a degree over cosmic distances could potentially return it to Earth's vicinity decades or centuries later, creating a delayed rather than eliminated threat. What does this all mean for humanity's future? The sobering reality is that asteroid impacts may represent what astrobiologists call a great filter, an evolutionary hurdle that most technological civilizations fail to overcome. If intelligent life is common in the universe but we see no evidence of widespread interstellar civilizations, something must prevent them from developing or persisting long enough to spread among the stars. Perhaps most civilizations never develop adequate planetary defense systems in time. They either allocate resources elsewhere, fail to coordinate globally, or simply run out of luck before their technology catches up to the threat. Our window to develop effective planetary defense might be closing faster than we realize. In the end, deflecting a planet-killer asteroid isn't primarily a question of physics or engineering, it's a test of foresight. Can a civilization recognize an existential threat that operates on geological rather than human timescales? Can we invest trillions in solving a problem that might not manifest for decades, but could end everything in an instant if we're unprepared? The true cost of deflecting a planet-killer asteroid isn't measured in dollars, energy, or engineering challenges. It's measured in our capacity for long-term thinking in the face of statistical, rather than immediate threats. And so far, humanity's track record on that front gives little cause for optimism.